Let's go back to RCNN now, okay, and then discuss the issues of RCNN and then see what is fast RCNN, faster RCNN is all about. And I hope you are already knowing about the issues, I mean, by now, right? So let's quickly review. So you have the input image, you pass it through a selective search algorithm which will give you 2000 region proposals. Then you kind of warp each of those regions, pass it through your CNN which is trained, and it will predict the class and then the bounding boxes. And of course then you use these bounding boxes, you pass it through non-maxima suppression to reduce the number of bounding boxes, and then you can evaluate the performance using MAP, which we discussed, right? And uh, this has few issues. Okay, so let's discuss. This is the first one. This RCNN, this guy, region based CNN, has to do forward passes 2000 times if there are 2000 region proposals. Of course, you can reduce the number of region proposals, but that's not good, right? That's really huge computation there. So let's make RCNN fast. I mean, that's a fundamental problem, right? So you kind of pass it through a selective search, how these proposals, then each of them you're passing it through the CNN. Can you do slightly better? Okay, the key idea is instead of running the crops or warped regions through the CNN, can we first pass the image through the CNN directly instead of cropping, and then the region proposals will be done separately. Of course, that part is not replaced, and then kind of warp the regions onto the features of the CNN, not onto the not like CNN being passed individually. Okay, so that's the idea. So pass the image through a single CNN, get the features, you do the region proposal on the image, then you warp these region proposals onto the features, not the I mean, that's as simple as that. And there is some technique known as ROI pooling. Okay, so that's what we do. ROI pooling of these bounding boxes, the region proposals onto the feature maps. Very interesting idea. And this idea has also been evolved with segmentation as well. So we'll discuss that later also when we talk about segmentation in that sense. But let's quickly go through it. So what is the idea? So you have a image, you pass it through a deep convolutional neural network. So you extracted few features and then you run the region proposal on the image, you extracted the ROIs, you project those proposals onto the feature map. Okay, so this is the idea. And then everything remains same. So the output of this then goes and have two outputs. One is for the classification, one is for the bounding box. So very important to understand this, right? So the deep convolution is used only once. In the previous case, it was used n number of times if n is your number of proposals or number of regions, right? But here we are kind of avoiding that. This one neural network which takes in the input image and produces the features, and you project the proposals onto the feature maps. So that's the idea. Okay, so each of these proposals, of course, you still need to map it to the feature maps, and that's actually done. And this is only I mean, basically, if you want, you can, I mean, I mean, ideally speaking, later on you still need to run a small network which is predicting the classification and the regression for each of the bounding box. That part is not avoided yet, but we really don't need a big network to now extract the features. So that's the idea. Okay, so that's the holistic kind of idea, and this is basically the header, the last few layers of the neural network in that sense, and the major convolution operation etc is happening on the image only once. So let me basically put it into few aspects. So there is one network which is feature extraction network. It is only done once. Then we need to do ROI pooling, which is like you map your proposals, the region proposals on the image onto the features of this deeper neural network. And then each of these features will pass it through a per region network, which is very lightweight, a few fully connected layers. where you predict the classes and the respective bounding boxes, because that is still you cannot avoid it, right? Because each of the proposals there should be a class and the bounding box associated with it. So that's the idea. Hope it's clear. And let me explain the ROI pooling in a more sense here. So you have the image, you pass it through a convolutional network, you have a feature layer here. So let's say the image size was 640 cross 480. I took it from the original paper, that's why some dimension here, color image. So 3 cross 640 cross 480. The feature map, the dimension is 512 features of resolution or height and width 30 cross 20. So you have a bounding box, let's say the region proposal like this. You will map it to the feature layer correspondingly. I'll explain this with an example so it becomes very clear to you. And then you kind of reduce it to the size that you want. The feature size may be 30 cross 20, but you will define the ROI pooling layer size to be, let's say, 2 cross 2. So there will be something like a max pooling which will be done eventually, which will kind of map it. So basically you warp your bounding box to the feature layer of the desired size that you want. So you can use it. So the importance of this is this. So the after ROI pooling, the region features, they will always have the same size even if the input regions have different sizes, because obviously your proposal regions are not of the same size, right? It will be different windows, different scaled windows. So each of these windows, you pass it through this ROI pooling, the output size will remain the same, let's say 512 cross 2 cross 2 irrespective of, because the mapping, this size will be different, because there will be a certain dimension associated with this, the which I'll explain to you in the next slide. But eventually what you want is, irrespective of the bounding box size of your region proposal, eventually everything should have the same size like this. Okay, so that's the idea. So this is for one region, you pass it through the lightweight CNN, which will predict the class and the bounding box. So that's the idea. So heavyweight is here, which will be used only once. The heavyweight neural network will just give you the feature layer, and that's all is done. The remaining is lightweight, which will kind of apply on this particular layer, and that's it. Okay, so that's the holistic idea here. So in torch vision, you have it as a single line command, the ROI pooling operation, which you can actually kind of give the input image and the boxes, the proposal boxes, and then you can even define the output size. Default is 7 cross 7 if I remember. And then the spatial scale also, how much you want to scale this, that also you can do it, and that's it. The output will be. So how it is used, something like this, you can actually go through this code, pretty simple. So you have the feature map. So this is that heavy neural network. So a very simple case here, a very simple convolution here. Okay, and then this feature map, you pull it using your ROIs. So basically this process is where your ROIs are mapped to your feature map. So these are the pool features. And then these pool features will be passing through the classifier and the bounding box regression. So that's the idea. I mean, very simple code here. I mean, can ignore if that makes too simple. So how this ROI pooling is done under the hood, let's explain that. So this is how it is done. Let's say I have few region proposals like this. It looks very nice, but it is most of the time ugly. But let's say few bounding boxes across this. So this is of size 512 cross 512. That's original image size, right? And the feature size probably maybe 16 cross 16. So you need to map each of these bounding boxes proportionally, right? This guy will come somewhere here. This guy will come somewhere here, and this guy will come somewhere here. But this height, so let's say I consider this as capital H, sorry, capital W, and this as capital H, and the same here. So let me put a small w and the small h. There is a scaling happening for W to capital W to small w here, capital H to small h here, and that scaling is nothing but this scaling 512 to 16. But you can also define the scaling just like I showed you in the torch vision code. So 512 by 16 is approximately 32. So there is a 32 kind of reduction happening for the width and height. But there can be a problem. This need not be exact mapped. It cannot be like exactly. So for example, I think this is clear here. So you can see here, this is coming somewhere in between, right? This is not mapped to this grid or this grid, so somewhere in between, which is not possible using a simple ROI pooling operation unless you do interpolation and map it exactly. So there may be some error which will be happening all the time through ROI pooling, which was kind of solved using something known as ROI align. So if you search in Torch Vision, you will also see ROI align, which we will discuss during segmentation. So that is something which is interesting, which was not available during the Fast-RCNN time. Okay, so please remember that. Okay, let's now zoom in this cat and see how it is happening. So this only. So you have approximately 200 pixels is your width in the original image, and 145 is I think this is 512. So don't forget that total. Okay, so 200 pixels is the width for the cat bounding box proposal, and 145 is the height for the same. Now what you need to do is you take this 200 divide by 32, because 512 by 16 the reduction is 32. So 200 by 32. I hope, let me zoom in here. Yeah, I think we can do that. Yes, perfect. So this you can see here. So this 200 by 32 is up exactly 6.25, but that's not feasible. It will be approximated as 6 if you are using a simple ROI pool. And similarly, the height 145, which was the original here, 145 by 32 is 4.53, but it is 4. Okay, and the center or one of the locations, let's say this corner location, will be like 9.256. Okay, so those are these center locations. But what is going to happen is you will kind of quantize this. So this red will become like the green region here, and this blue, whatever the blue, will be completely gone. Okay, so the final, let me just zoom out. I cannot kind of use a pointer here. I'll mark it and then I'll zoom it again. So let's use which color? Probably yellow. I think it's not used. So ultimately you will be getting this, or I think it's very difficult to draw. So let me explain using the color names actually. Ultimately you will be getting this green plus this orange as your ROI pooled output, and this blue region is completely gone because of this quantization. But if you use ROI align, there is some interpolation under the hood which will kind of fit exactly into like 6.25 cross 4.53, not 6 cross 4. Okay, so that's the idea. I hope the crux is understood. So basically you map it, the proposal, onto the feature layers individually. So you do it for all the 512 layers, and you have to do it for each of the bounding boxes. Then what you do is you just crop this feature and pass it through your lightweight network, which will kind of predict the class and the bounding box for this particular region. Of course, the class is cat here and the bounding box is there, and all the other things which you use for RCNN will remain the same, like the scaling and the sender translation for the ground truth, and all those things will remain the same because everything is kind of consistent. The only difference that we did is we made life easier by having a single network like this, which will kind of get us the feature layer. Then you use the region proposal bounding boxes to warp it to the feature layer, and then this will be passed on to your lightweight header, which will predict the class and bounding box for each of these region proposals. So that's the idea. I hope it's pretty easy to follow. Okay, so now, yeah, I think this is already mentioned, so I'll just skip this part. It's already there. Now let's do a comparison between RCNN and Fast-RCNN. The left hand is RCNN and right hand is Fast-RCNN, just to make sure we understood both. So here what we are having is you have the input image, you do the region proposal, this remains same for both, there is no difference. But in the case of RCNN, you crop each of the region proposal pass it through a CNN, a heavyweight CNN. So each of the crop region, so if you have 2000 proposal, this RCNN has to operate 2000 times, and that's the killer. It still predicts the class and the corresponding bounding box, and don't forget the mapping or the scaling of this bounding box back to the image space. Now if you see the training time 84 hours and testing is 8.75 hours. This is not for one image, is for set of images. This is on the COCO dataset if I understand correctly. Now moving to the Fast-RCNN, we moved this guy slightly earlier. So you have the deep convolutional network which will give you the feature layers. You still need to do the region proposals, and that region proposals should be kind of mapped or pooled to the feature layer, and each of those pooled regions you will pass it through a lightweight network for the prediction of class and the bounding box. Okay, so that's the idea. So now you see the timing. This is only 49 hours, and if you exclude the region proposal you only need 47 hours. So the network time is actually just 47 hours for training. You almost halved, right? Moving away from RCNN to Fast-RCNN, you saved almost like half time, right? That's a huge time, and inference is really good, like 2.3, and out of that 0.32 is the time taken for region proposal, because that's done on CPU most of the time. Okay, but huge savings, right? That Fast-RCNN is definitely a killer of RCNN in most of the time. But in the lab you will be doing RCNN and Fast-RCNN from scratch to understand how it works. You measure the speed and see how good it is, the speed up and so on. Okay, so that's the idea. Now let's move on. Okay, can we further optimize? The question, that's the motivation towards faster RCNN, right? So can we further optimize? So here the idea is, instead of using the selective search algorithm, which is still taking some time for the region proposals, can it be replaced by another neural network just for the region proposals? Pretty trivial kind of thought, right? But that's actually quite powerful. So let's see that. So this is the architecture, the faster RCNN. If you want to read up more details, please see this paper here. Very beautiful paper. So the idea is, you have the image, you kind of pass it through convolutional layers similar to the Fast-RCNN. You have feature map. So this is the heavy load here, and then from the feature map you have a bypass here. You have a region proposal network. So you are going to predict the regions using a region proposal network instead of a selective search algorithm. And this region networks, if I expand it, it looks like this. It can actually predict bounding boxes. Okay, and they will have, so k anchor boxes, so k predictions will be there, and each of these k will have two predictions for classes. So here not the, so please, there's some confusion which will always happen. So here this is not the class for final prediction. Okay, so don't confuse this with the final classifier which will have the classes for the objects like cat or dog or house or whatever. This is basically just two values, z0 and c1. One is the background class and one is the object class. So it just tells you whether the object is present or not. Binary classifier kind of. So for each k and each anchor box, it will have two values for classes, one for background and one for object, and then four values for the coordinates of this bounding box or region proposal. So the region proposal will have binary classes, one saying that it is a foreground class or a background class, an object class or a background class, and four values for the coordinates of the proposal. Okay, so if you have k anchor boxes, you will have 2k scores because two values for the classifier and 4k for the coordinates, right? So that's the idea. Okay, so you have this feature layer, it will be mapped to a neural network, and that neural network will be having an intermediate layer like 256 dimensional, which will give you like 2k scores and 4k coordinates in that sense. Okay, so that's the idea, and don't get confused. This classification score is just to tell you if it's an object present in that region proposal or it's basically a background, and this is determined through your ground truth. Don't forget that, because ground truth is telling you whether it's a background object or a foreground object, right? So that's from the ground truth. and then the coordinates also, right? That's also needed. So once you have this will be passed through an ROI pooling, because you still need to kind of pool this from the feature map, and then you will pass it through a classifier plus a regression here, which will be the final layer. So it's a bit complicated, but it's not difficult to understand, right? So it was a gradual step, right? You replaced the selective search algorithm now with another neural network. So that's the idea. Now the training will have 4 losses. One is of course the loss for this classification plus this regression, and the other one is for the final classification plus regression, which we always used to do. Okay, so the RPNN uses k different anchor boxes at each point, and then each output there will be a classifier plus bounding box, which we told, but then the final loss will be this classifier loss plus this bounding box. This classifier will be just a binary classifier. The ground truth is object being background or foreground, and this bounding box, the ground truth will again be the ground truth whether it's an object or not. I mean those coordinates of those bounding boxes. And then the final loss will be these 2 losses plus the final classifier plus the final regression loss. So that's the idea. So what is the savings that we are going to get? The RCNN used to take 49 hours inference. Fast RCNN reduced it to like 2.3, and faster RCNN reduced it to be like 0.2, because now you don't need that selective search algorithm also. So this is the idea that, I mean, this is the advantage if you move from RCNN to fast RCNN to faster RCNN. Faster RCNN from scratch is difficult, so you'll be leveraging the pre-trained models in Torch Vision in your lab, but it's fun experiment to do that, and you will be calculating the MAP scores for different IOUs and all those things, and you'll see the result as well. Okay, so all versions of RCNN has 2 stages. That's why it's called, I think we need to see why it is double stage object detection, right? All versions of RCNN has 2 stages. The first stage is region proposal, right? The first stage is basically the region proposal plus the backbone. It will run once per image. Please remember that. Okay, it will run once per image. The second stage consists of the ROI pooling plus the prediction network, which will be running once per the region. Please remember that. Okay, so you have the image. Let me write it here. This will be going to a region proposal, and the same image will go through a backbone, right? For RCNN, of course, this backbone will be later, but generally this is the idea. So this will give you regions or initial guesses for the objects. This will be passed through another neural network, lightweight, and that will give you the class plus the bounding box for the final predictions. And of course you need to do the non-maxima suppression, that's very important, as well as you will evaluate everything through mean average precision. Don't forget those things as well. Okay, so that comes us to the faster RCNN kind of thing. Do we really require 2 stages? No, and that's why we have single stage detectors like YOLO, which we will cover up next week. Okay. Some further for self-study, these are advancements beyond this faster RCNN. So cascade RCNN, where you have multi-stage IOU based training, because we never had IOU in the loss function for RCNN variations, but you can actually bring IOU also. Then you have detector R, I think there's a spell here, detector RS. So recursive feature pyramid and switchable. So all these concepts we'll be discussing later also, like at-risk convolution during the segmentation. So we'll have, so feature pyramid is something again we will have a discussion next week, so I'll discuss about that in detail later. Then something known as Libra RCNN, you can take a look at it, sparse RCNN, so these are variations. And then of course you can use transformer as the backbone instead of a convolutional neural network like VGG or ResNet. So there is work in that direction from Facebook, which is the very first towards their class of object detections known as detectron. Detectrons are famous object detection models from Facebook. So you can do these as self studies. Of course, this will not be assessed, so it's optional, but highly encourage you to go deeper in this. I'll correct this spell here. Okay, so just to summarize our this week, so object detection, though it appears easy, it is not a simple mere extension of classifier, it's a harder problem. Okay, so you'll have classification plus bounding box, which will give you the coordinates of that class, right? So that's as simple as that, but it's not that trivial. Lot of refinements possible, infinite. You have backbones, right? You have a backbone network which can be VGG or ResNet or transform or any modern network that you can choose from. That's why it's very important that you have a thorough understanding of what you studied in the previous trimester, because that sets you for this not previous trimester, I keep saying that, sorry, previous weeks, that sets you for the upcoming weeks actually. Okay, so you can have pre-training, you can actually have n number of ways you can do the image transforms and data sets, the annotations, all those possibilities, right? You can have the later part. So backbone is the first part, the head and neck is basically the one which takes all the regions and predicts the class, and so you can have variations for that as well, the RCNNs and the variants on that. And then you have many concepts related to object detection which we discussed, like anchor boxes, how different formats represent them, IOU intersection over union, non-maxima prediction, it has a lot of variations you can read up. Then mean, average, precision, I hope nobody will forget that, and then the losses associated with it. Okay, you can also do many things to speed up. So please read up these two papers linked here for your advanced self-study. Many ways to speed up your object detection other than going from RCNN to fast RCNN to faster RCNN. Okay, these are all possible to speed up during training, but inference speed up is still tough because you still need to do the non-maxima suppression and so on. So it's still tough. Okay, so thank you, and if you have any queries, you can always post in the discussion forum, and or you can email me in this. I always encourage you to put in discussion forum first, because your questions may be others' questions as well. Okay, thank you. See you all in the lab.